So let's start. Uh, the next chapter that we're going to do is known as equilibria or chemical equilibrium. Chemical equilibrium. You can also write chemical equilibrium or just equilibrium. That's the chapter's name. What we want to study in this, the topics that are included in our syllabus. It's a very long chapter if you consider all the details that you need to learn about equilibria. But what's included in AS is, first of all, you need to know what a reversible reaction is. So we'll start from reversible reactions. All right. The second thing that we need to know in this chapter is what equilibrium is, what is equilibrium, and what is dynamic equilibrium. There's two types of equilibrium. Just the difference of conditions of how the equilibrium is basically established. So that will be equilibrium and dynamic equilibrium. That's what we need to know. Apart from this, we need to know that equilibrium is only established in a closed system. That will study a closed system. So let's write closed systems. What are closed systems, right? And apart from that, you need to know what controls equilibrium, and that's the Le Chatelier's principle. Le Chatelier's principle, right? How an equilibrium behaves if you like try to disturb it by any external force. All right. And then factors that affect equilibrium, again, that is going to operate on the Le Chatelier's principle. Factors affecting equilibrium. After we're done with all this theory, then we're going to move on to our calculations part. That is about equilibrium constants. Equilibrium constants. And the two constants that we're going to learn over here is one is Kc and the other one is known as Kp. All right. And for what do we have to do for these constants? We have to learn how to write their expressions and some questions related to calculations. All right. So this is most probably the whole chapter. This is all related to equilibrium, but in the chapter equilibria, you have some more topics that are included. All right. After all this, we are going to study acid-base equilibria. That will be included in this chapter. Acid-base equilibria, in which you have to study types of acids, and bases. What are Bronsted, Lowy, acid-base pair, or acid bases. That's what you have to learn over here. And apart from that, you have to learn about titration curves, which we left out in the chapter of titration, so that when we study acids and bases properly in this chapter, then we'll be able to draw the titration curves. Okay, so that's the titration curves. That would be our last chapter. And apart from this, in equilibria, you'll have to learn about Hebel's process and the contact process and what their conditions are. That's what you have to memorize in that portion. All right.
Yeah.
And also in this, you'll have to learn about pH and ranges of pH. You don't need to know how to calculate pH. You just need to know the pH ranges. For an acid, it should be below 7. For a base, it should be above 7. For a neutral solution, it should be 7, right? So that's what you'll have to learn. Just the ranges for the titration curves and just an idea of what a pH would be for an acid, for a base, for a neutral solution. That's all you need to know. All right. So
Yep.
this is all our topics. These are all our topics that we have to learn in this chapter. So we'll start with reversible reactions, but we let me lay the line over here. So let's start with the first topic, that is reversible reactions. Now, reversible reactions are reactions which can proceed in forward and backward direction simultaneously, both of the directions. So a reactant could go into a product, right? And a product could go back and form the reactant. So it could go in the forward direction and it could also go in the backward direction. These are known as reversible reactions. You could either make products from reactants or reactant from product. So it proceeds in both directions. So we can define reversible reactions as reactions in which or reactions which proceed in forward and backward direction. Or which can proceed in forward and backward directions. All right, so they can go forward and they can go backward. But before this, we haven't heard of any reversible reactions. What we used to do were irreversible reactions. Irreversible reactions. What are irreversible reactions? All the equations that we've written up till now had an arrow looking like this. What does this arrow mean?
Then you
This
can't
means
go
that
back.
you can only go into the forward reaction. So only a forward reaction occurs. You cannot go in the backward direction or form reactants again from products. All right. So
Yep.
this means that 100% complete reaction takes place and all the reactant converts into what? Product. So if this reaction were taking place in a beaker, for instance, at the end of reaction or in the start of the reaction, what would you find inside the beaker? The reactant, right? You would put the reactants inside the beaker. For instance, the reactants were A and B, right? So initially in the beaker, you put two reactants and then the reaction proceeds and A and B start reacting to produce C. Now, since this reaction is not reversible, it is an irreversible reaction, it will always go up to 100% completion. All these reactants will be consumed. And at the end of reaction, what should you find in the reactant mixture or in the beaker? You should only find C, right?
Yep.
Because all of the reactants will react together to form the product and only the product will be present at the end of reaction. No reactant will be present over there, right? That means a complete reaction took place, all the reactant converted into product. And now you cannot go back from these reactants to, sorry, from the product to the reactants because it's only proceeding in only one direction, right? So at the start of reaction, let's make a diagram of this too. So before reaction, you will have a beaker in which you have A and B. And then after reaction, you won't find any A and B, you'll find your product only. All right, so this is a 100% complete reaction in which you find product at the end of a reaction. Are we clear till here?
Yep.
But the irreversible reaction, what happens in the irreversible reaction? That it proceeds in both directions. Some reactants convert into products and a portion of the products does convert back into a little portion of the reactants, right? So what's happening in reversible reactions? Reversible reactions is that initially before reaction, you'll again have just the reactant. Before reaction, you'll only have the reactant. For example, I'll label this as reactant goes into product, right? So what is this over here? This is a reversible arrow, all right? Whenever you have a reversible reaction, you make the reversible arrow instead of the arrow that is unidirectional or one direction, all right? So this is a reversible arrow, reversible reactions arrow. You have to make sure you make this arrow. So before the reaction, you have only the reactant over here, right? Now, as the reaction proceeds, these reactants start converting into products. So let's go midway. Midway of the reaction, you have some reactant and some product in the reaction, right? But since not all of the reactant will convert into product and 100% complete the reaction, this reaction is never 100% completed. So this is the first very important point. Never 100% completion of a reversible reaction, or a reversible reaction never completes or never goes up to completion. All right. So some reactant is still here and we have formed some product. At the end of reaction, what you'll find over here is, again, you'll find some reactants and some products over here. All right. You won't just find the product, you'll still find the reactants as well as the product in the reaction mixture. Whereas in irreversible reactions, you only find the product. All of the reactants converted into product. But over here, not all of the reactant converted into product. Still, some reactant remains, some product remains. All right. Are we clear
Yep.
till here? Right?
Yep.
So the reaction never ends. This is also very important. In irreversible reaction, the reaction goes up to 100% completion, right? So it ends after reactants are consumed fully. Right? So an irreversible reaction ends as soon as the reactants are consumed. But a reversible reaction, it never ends. It will keep on going. It will keep on going. These reactants after some time will go into products, and at the same time, some of the portion of the products that were made will go back and form reactants. So it's a continuous process. It never ends unless and until you apply some external force and try to quench the reaction over there. Quenching means stopping abruptly. All right. So unless and until we stop this reaction by using some external force, this reaction is going to keep on carrying on. So reversible reactions, this is the second important point, never end. All right. So reversible reactions never end. So are we clear about what a irreversible reaction represents and what a reversible reaction represents?
Yep.
So these are the two types of reactions that are going to take place. All right. So now let's go into detail of reversible reactions. So we talked about reversible reactions in which reactants initially try to form products, and when some amount of products is formed, a decent amount of product is formed, what the products do, they start converting back into reactants. But there are conditions for reversible reactions that need to be present in order for a reaction to become reversible. Remember that reversible reactions can only be established in a closed system. All right. A closed system is very important for a reversible reaction. Why? Because if the system is not closed, maybe some products escape, right? And to go back, you need this product to make the reactant. And if that if that product escapes from there, you can never go back. You can never go in the backward direction. I'll give you an example to explain this. But a closed system is, you can call it a sealed container. A sealed container in which no more amount of reactant or product can be added or removed. Can be added or removed. All right. So it's a sealed container in which initially you put some part of the reactants. They react together. None of the products are lost. None of the reactants are lost. They're just interconverting into each other. So that's a closed system, and you do not add any further reactant from outside. You cannot remove any reactant from the outside because the system is closed, right? So a closed system, you cannot add anything, you cannot remove anything. But what you can do is you can add or remove energy. That is allowed. You can add or remove energy, or energy can be transferred or removed, but the amounts of the reactants or products, they cannot be added more or removed, because that's a closed system. When the system is closed, nothing more can be added or removed from the system, but a transfer of energy can take place. That is transfer of energy can take place. All right. Are we clear what our closed system is?
Yep.
Now let's take an example of a reversible reaction, but we'll keep the system open initially. All right. So let's take an example. Example that is of an iron oxide or iron reacting with steam. All right. So if we have Fe solid that reacts with steam, that is H2O gaseous, that will form its oxide. Metal plus water forms metal oxide plus hydrogen gas. So it forms its oxide, that is Fe3O4, which is a solid oxide. Again, it's an ionic compound, that's why it's solid, and produces hydrogen gas. Now, this is a reversible reaction. That means these products can go back and form this. But if I keep the system open, the reversible reaction can never be established. Why? Because in order to go backwards, these two things must be present over here, right? So that they
Yep.
can go back and form H2 and iron solid again. But I've kept the system open. How do I know that? Because the way I'm conducting the experiment is that I had iron solid over here. This is my Fe solid. This is a glass tube that is open from both sides. From this side, I'm inserting steam. That is H2O gaseous. This is the reactant. This is also the reactant, right? In this equation for the forward reaction. Now what happens is that iron oxide is being produced here. Let me make iron oxide with, for example, let's make it with purple. The iron oxide over here, when steam passes over this iron solid, the hot steam reacts with the iron solid, produces the Fe3O4, right? This is the product Fe3O4. Since it is a solid, it doesn't move from here. Fe3O4. But it also produces H2 gas. And this H2 gas, since it is an open system, it is swept away out of this system by the steam that was being, by the stream of steam that was being inserted. Right? So you lost the mass or the amount of H2O that was being produced since it is an open system. So if you produce H2, but you've lost it to the surroundings because the system was open, can you now go back in the backward direction?
When the system is open?
Yeah, when the system is open, can you go back in the backward direction? We
No.
cannot go in the backward direction. Why? Because for the backward reaction, these two were the reactants, right? And we lost one of the reactants due to the open system. It was lost into the atmosphere. So now it's missing over here. So that's why this reaction right now can never go in the backward direction, right? So to go into the backward direction, the conditions must be met that the system must be a closed system. This is not a closed system, it's open from both sides. So the H2 gas that was produced, if we contain it over here, then there are chances that it can again go back in the backward direction. But it was open, this stream of H2O gaseous, it will sweep away all this hydrogen gas that is being formed and take it out of the system because the system was open. All right.
Yep.
But if you start from these two things, then you can see that this reaction can go in backward direction. And that is, again, I'll keep the system open, but from here, I'll give it a stream of H2 gas instead of water, and I'll keep the iron oxide over here. Now, this is a reduction reaction in which the Fe3O4 solid now reacts with the stream of hydrogen gas and it is reduced and converts back into iron and water. But that water is in steam form. So now I'll label these as green and I'll label the other side as purple so you know what I'm referring to. All right. So now the green reactants will start to be forming. So H2 reacts with the iron oxide and goes to Fe solid and H2, right? So you'll start forming Fe solid over here. So the iron oxide is reduced by hydrogen. It forms Fe solid, but the H2O formed is again in gaseous state due to high temperature. So the H2O formed over here, again, it is in gaseous state and the system is an open system. This H2 stream will sweep away all the H2O formed and take it out of the system, right? So our reaction should be Fe3O4 solid is reacting with H2 gas and going to form Fe solid plus H2O gaseous, right? So again, since the system was open, if I do the backward reaction, the same thing happens. Now these two cannot go in this direction. Why? Because the H2O that was produced was removed from the system. It wasn't contained by the system, right? So now this is an
Yep.
example of how a reversible reaction can also act as a irreversible reaction if the conditions for a reversible reaction are not met. So it is going in the backward direction like this in this reaction, right? But since again this and this both these products were formed and these are supposed to be reactants for the backward reaction, but one of them was lost to the surrounding due to the open system, this reaction again cannot go in the backward direction. Although it was happening when we were going in, conducting this reaction in the presence of Fe solid and H2O and the example that we've done before this, right? So again, you lost one thing. So it was an open system. You lost the H2O gases that was required with the Fe solid to go in the backward direction. So now you cannot go into the backward direction. This remains a unidirectional reaction. It only goes forward. Are we clear up till here?
Yes.
So now, if this reaction was converted in a was conducted in a closed system, what would happen? Same reaction in closed system. I'll make a big diagram so we can move things around over here. So let's start with the H2O gaseous stream, right? And the iron solid that was present over here. Let me not write H2O gaseous stream. Let's make this a closed system. And before closing the system, we put in over here Fe solid. We have Fe solid over here. We have H2O gas over here. And initially, do we have any products initially? Or do we have only reactants in the system? Initially, at time zero,
Reactants.
only the reactants, right? Now these two things start reacting and start to form what? Products that were iron oxide, Fe3O4 solid, and what are they forming? H2 gas, right? These are the products that are forming in this closed system. Again, are these products allowed to leave the system? This is a closed system.
No.
They cannot leave the system, right? And as we saw in the examples above, that Fe3O4 and H2 can undergo a reduction reaction, a redox reaction to form Fe solid and H2O gas again, right? So now, since they have not left the reaction mixture, these two will start reacting together to form the reactants again, and this reaction can now proceed in the backward direction. Because it's a closed system, both these were available in order to form or in order to conduct the backward reaction, they now can conduct the backward reaction. All right?
Yep.
Are we clear till here?
Yes. Yep.
So now what happens is, initially you had the reactants, right? Now after every second, some product is being formed, right? Some of the products are being formed after every second. That's the forward reaction. And in the same second, whatever the product formed at that time is, whatever the amount of product at that time is, some of that product also is going backward and conducting a reaction to form the reactants as well, right? So this is where you'll start to learn about an equilibrium. What is an equilibrium? So this is our forward reaction, and this is our backward reaction. Do you understand what rate is?
Yeah.
What is the rate of reaction?
How fast the reaction occurs?
Yeah. Change in concentration of reactant or product divided by time, right? That is rate. It tells you how fast the reaction is. If rate is very, if rate is the value of rate is very large, that means the reaction is very fast. It takes very less time to convert into reactants, convert the reactants into products or product into reactant, right? So now,
Yep.
what is equilibrium? So initially you had reactants, they started converting into products, and you started, the product started to accumulate in this closed system. Now, what they decided was that after every second, a lot of product is being formed, and it is easy for the product to go back and form some reactants. So now the product, what does the product do? It starts forming some reactants after every time. All right. After every second, it starts forming a little bit of reactants as well. So the reaction is proceeding in the forward direction, and it is proceeding in the backward direction. Now they both will decide the forward direction of the reaction and the backward direction of the reaction. Both will come to terms, and they will decide that after every second, how much of the reactants should convert into products and how much of the product should go back and form some reactant. That is known as our equilibrium state. All right. So an equilibrium is established. So what is equilibrium? Equilibrium is when the rate of forward reaction becomes becomes constant. Let's say when the rate of forward reaction and backward reaction becomes constant. That's a state of equilibrium. So let's try to explain this. So you have reactants. Initially, all the reactants are just converting into products, right? So this was the forward reaction. Now what happens is that after some amount of the product is being made and reactants are still converting into product, the product decides that since I can go in the backward direction and it is a closed system, let's start forming a little bit of reactants as well from our side. All right. So the product starts going back and forming what? Some reactants as well. Now, both of them initially try to come to terms with each other. The reactants ask the products, how much product should I make in every second, right? So every second, how much product should I make on the right-hand side? And the products ask the reactants, how many reactants should I make after every second? So then they come to terms, and then they establish an equilibrium in which both of them now have decided that after every second, how much products will be made, yani the forward reaction will be conducted, and in the same second, how much product should go back and make some reactants. So they come to an agreement, right? And that is the state when equilibrium is achieved. The rate of forward reaction becomes constant. It has been decided now that the reaction will proceed 30% in the forward direction. They have decided. All right. After every second, in every second, 30% of the reactions go into products. And then in every second, the reactants, the backward reaction has also become constant. So the products have decided that 70% will go back. Out of all the product that has been made, only 70% should go back and make reactants again. All right. So
So
now
not
forward,
50-50.
uh, because 50-50 is a different thing. All right. That's known as dynamic equilibrium. I'm coming to that. All right.
Okay.
Equilibrium is when rate of forward and backward reactions have become constant. They can be constant by 30-70, or They could be, but do you understand how they become constant? Right?
Yeah.
They've decided that 30% of the reaction from now on will convert into product, or the forward reaction will be 30% and the backward reaction will be 70% in every second. They've decided, they made it constant. This is a state of equilibrium now. The same thing again can happen if the reactants decide that will go 70% and form the products. The forward reaction should be 70% in every second, and the backward reaction should be 30%. This is also a state of equilibrium because now the forward and backward reaction have become constant, right? This split could also be 40% forward and 60% backward. It's still, again, the reactions and products have made it constant. That forward reaction would be 40% in every second, and 60% of the products will go back and form reactants in every second. So it's constant. Equilibrium has been established over here. All right. The equilibrium has been established because the rate of forward and backward reaction have now become constant. You're not just going in the forward direction or not just going in the backward direction. They have decided or come to an agreement that how much reactant should now convert into product, and how much product should go back and make reactants in every second of the reaction. All right. This split could also be 90-10, 90% forward, 10% backwards. This split could also be 20-80, 20% forward, 80% backward, or 80% forward, 20% backward. Right? But the point is that the forward reactions rate is constant and the backward reactions rate is also constant. They've decided now and established an equilibrium. Initially, this wasn't happening. Initially, the reactants were only converting into products. But when the products started to accumulate, they decided that since it is easy for us to go back and form the reactants, why not do that in this closed system? Right? So now they start going back. So initially, let's say that this was 100% and this was 0% at time 0, or initially when the reaction had started. But then as the reaction proceeds, this becomes 90% and this becomes 10%, the backward reaction. Now, if they decide that this should be the state of equilibrium, that the reactant should go and form 90% products and product should just 10% of the product should go back and make reactants, it will be a state of equilibrium. But if they start changing again, the forward reaction becomes 80% after a while, and the backward reaction becomes 20% after a while. So they haven't achieved equilibrium up till yet, right? Because it's still changing. They're still deciding. And then this becomes 70% and this becomes 30%. So it's still
So it
changing.
doesn't matter that the total is going to be 100. It just has to be
Now
constant. So
that
it
this
can't
is
be like
just a
changing.
way of trying to explain what's happening. There's no percentage of it. All right. I'm just trying to
Yeah,
explain
okay.
how the rate is constant. All right. These percentages are not anything or not a real thing over here. All right.
Okay.
It's just a way of
Yep.
representing rate, what's happening in the forward, how much reaction is going forward, how much reaction is going backwards. All right. And then when you look at it after, for example, in the first minute, you saw 90-10, 90% forward and 10% were making reactants again. So in the backward action, it was 10%. Then after 2 minutes, you saw that it changed to 80-20. Then after 3 minutes, you saw that it changed to 70-30. And then after 5 minutes, you saw that it changed to 60% forward and 40% backward. Then you came back after like 10 minutes and you saw that this hasn't changed. You came back after 15 minutes, you saw that this hasn't changed. So what does that mean? That an equilibrium has been established now. Both reactants and products have decided how much we're going to produce product or go in the forward direction and how much will go in the backward direction in every second or in every minute, for example, over here in the example that I've given you. So now this isn't changing, right? They've become constant. Before this, they were changing. So let's make a table for this. So I start this reaction And what happens at time zero? I'll write this as the like this, okay? Forward and backward reaction. Or let's write it like this. Forward and backward. Let's make a table so it's easier for you to understand how this reactant established equilibrium. So let's say at time zero, initially, nothing was happening. When the time started and you reach time 1 minute, at 1 minute, you saw that 90% was going forward and 10% was going backward. Now, has equilibrium been established? You'll have to come after some interval of time and then check again. If it stays the same, that means equilibrium was established and they decided that 90% would go forward and 10% reactants would convert back into products. All right. But you came after 1 minute again, and then you saw that this has changed. 80% is now converting into product. The forward reaction is 80% and 20% is backward reaction. So it changed. That means equilibrium wasn't decided over here, but equilibrium wasn't established over here, right? So after when you come back at 3 minutes, you see that it has changed again. It's 70% forward now and 30% backward now. So you know that equilibrium was not established over here either. They were still deciding, they were still coming up to agreement that where that rate should be set or be constant for equilibrium to be established. But when you come back after 4 minutes, at 4 minutes, you see that the reactant again, forward reaction has become 60% and the backward has become 40%. Then you come back after 5 minutes, and then at 5 minutes, you saw that it's still 60% and 40%. Then you come back at 6 minutes, and then you see that it's still 60% forward and 40% backward. What does that mean? Now these percentages for the forward and backward reaction, or the rates of forward reaction and backward reaction, are not changing. What does that mean for the rate? What has the rate become? It has
Constant.
become constant. So that means that equilibrium was established now. This is equilibrium established here then, right? Because at this time, so this means that equilibrium was established at this point in time, right? They both decided that from now on, we'll go 60% in the forward direction and 40% in the backward direction till somebody comes and stops this reaction, because reversible reactions never stop, right? So this is where equilibrium was established. The rate of forward and backward reaction became constant. All right.
Yeah.
But if the rate of forward reaction and backward reaction become equal, what does that mean? So that is known as dynamic equilibrium. What is dynamic equilibrium? It is known as when the rate of forward and backward reaction becomes equal. It does get constant, but the forward and backward rate are equal. That's when dynamic equilibrium is achieved. All right. So what are the
Yep.
conditions for dynamic equilibrium? That is, the rate of forward reaction would be how much? 50%, and the backward reaction would also be 50%. Now the rates are same, right? This is when you call it dynamic equilibrium. The other splits of equilibrium, or the other ways that equilibrium can get constant, are known just as equilibrium. For 60-40, it's going more in the forward direction, less in the backward direction. Any split, all that I've written over here, they're all just equilibriums. But when they become 50% forward and 50% backward, that's when you call them dynamic equilibrium. That's when dynamic equilibrium was achieved, because the forward reactions rate and the backwards reactions rate had become what? They had become constant and equal to each other. Okay.
Yep.
All right. But there's one more thing that I'd like to add into equilibrium. And that is, equilibrium is when the rate of forward or and backward reaction becomes constant in a reversible reaction, right? Because only reversible reactions can go backward and forward. So you need to mention reversible reactions, right? So in a reversible reaction, but there's one more thing, and that thing is, hello, can you still hear me?
Yeah. Yeah, I can.
The screen is stuck. I think it should wait. Just wait a second. The screen is like lagging a lot.
Oh, okay. No worries. Uh, it's lagging. So is the screen moving easily, or is it Yeah,
lagging?
I see it moving.
Okay. So where was I? Yeah. So so equilibrium was when the rate of forward and backward reaction becomes constant in a reversible reaction. But remember that the concentration of the reactants remains constant. The concentration does not change for the reactants. So let's add, and the concentration of reactants and products remains constant. That does not change. All right. So you need to add this. So let's go to dynamic equilibrium. So we said that when the rate of forward reaction and backward reaction becomes equal in a reversible reaction, and the concentration of reactants and products remains the same. That does not change. Now, to explain the second part of this definition, I'll have to make a table again. All right. So let's do that for dynamic equilibrium. You started the reaction at time zero. You started the reaction at time zero, and you had 100, let's say 100 grams of the reactant, and 0 grams of product were made right now. Right? So initially, what does the reactant do? It starts going into the forward direction, right? It starts going in the forward direction and product is being formed. So that makes it, let's say at time zero, it was like this. At time 1 minute, it became 90 grams, and this became how much? 10 grams, the products. Then at 2 minutes, this is time. over here. At 2 minutes, this became 80 grams and this became 20 grams. Now, do remember that this reaction is proceeding in both directions. All right. So out of this 20 grams, some is going back into the reactants, and out of this 80 grams, some is going back, going into the product side. Some mass is converting into products, some mass of the products is converting into reactants. At 3 minutes, you go and you see that 70 grams and the reactants are 70 grams and the product is 30 grams. And then after 4 minutes, you see that it remains the same. At 5 minutes, you see that they remain the same. What does this mean?
That the rate is constant?
Yes, that does mean that the rate is constant. Can I say equilibrium has been established?
Yep.
So equilibrium was established. That is correct, right? Equilibrium was established. That we know now. That the rate of forward and backward reactions have become constant. But now let's talk about the reactants and the products, their amounts at equilibrium. Are the amounts of reactant and product now changing when equilibrium has been established? Are they changing or are they constant?
No, they're constant.
Yeah. So can I say the concentrations of reactants and products are now same? Sorry,
Yep.
not same, they're constant also, right? They're
Yep.
not changing anymore. But has the reaction stopped?
No, it's still going on.
Yeah, it's still going on. It's still going in the forward and in the backward direction as the time passes. But what are they doing? They had established an equilibrium, so they are maintaining these levels of reactants and products on at this equilibrium. All right. So the reaction is still going forward, still going back in the backward direction. It's still proceeding. But what are they doing? They're keeping the concentration of the reactants and products constant. They're not changing it anymore. Before this, they were changing it. 100 gram, 0 grams. 90 grams, 10 grams. 80 grams, 20 grams. When they reached this point, equilibrium had been established. The rate of forward reaction and backward reaction had become constant. So now it's their job to make 30 grams. It is compulsory for them because equilibrium has told them to, that it is compulsory for you to maintain this 30 grams of product and 70 grams of reactant on the other side. So the amounts of the reactants and products, or the concentration of the masses, are not changing anymore. But the reaction is still proceeding in the forward and backward direction. Are we clear about the second portion of the
Yep.
definition? Yeah. So that's why what is dynamic equilibrium? When the rate of forward and backward reaction have become equal in a reversible reaction and the concentrations of reactants and products remain the same. This does not mean that they are equal to each other. This just means that whatever was decided at equilibrium, now they remain that value of concentration over there. All right.
Yep.
And in case of dynamic equilibrium, let's explain dynamic equilibrium. When equilibrium is established, before reaction, it was 100 grams, 0 grams, right? At dynamic equilibrium, the rate was 50% forward, 50% backward. So 50 grams over here and 50 grams of product over here. Now, does the reaction stop?
No, it doesn't.
It doesn't stop. It is at equilibrium. It is still going 50% forward after every second. It is still going 50% backward after every second. But they have decided that at equilibrium, these concentrations of the reactants must not change. Now they should remain 50 grams. All right.
Yep.
So how do we define dynamic equilibrium? It is when the rate of forward and backward reaction becomes equal. That's dynamic equilibrium. And the concentration of reactants and products, what do? They do not change. They remain constant. All right.
Yep.
At equilibrium, when equilibrium has been established. Before that, they were changing. They were finding the best possible equilibrium state. When they found that, now they maintain these levels at equilibrium. All right.
Yep.
So that was dynamic equilibrium. And after dynamic equilibrium, We've done closed systems. Now, what I need to do is I need to make a graph. Let's move on to the graph for dynamic equilibrium. So in this graph, for any reaction, what you're trying to do is you're trying to compare the concentrations of reactants and products versus time. So this is the concentration on the y-axis in mole per dm cube, and it is for the reactants and products, both of them. So starting from time zero, and this is the time, and it can be in seconds, it can be in minutes, but the standard unit of time is seconds, right? So if I ask you at time zero, what should be the concentration of reactants? It should be maximum, right? The reactants at time zero, when the reaction hasn't started there, and they have the maximum concentration, right?
Yep.
They haven't reacted any amount of reactants hasn't reacted yet, right? And at time zero, what should be the concentration of products? No product has been formed right now. It should be zero at time zero. Now what happens is that the reaction starts to proceed. Now these reactants, what the maximum amount of reactant that was present initially at time zero, now this starts converting into what? It starts converting into product, right? And the product starts to increase. So when these reactants or the amount of reactants or the concentration of reactants starts reacting to form product, what should happen to the concentration of reactant? Should it decrease or increase as it reacts?
Decrease.
It should decrease. So the reactants start to decrease with time, and then there comes a time when this concentration becomes constant. What is that time when the reactants concentration will become constant? That is when equilibrium was established, right?
Yep.
Same goes for the product. The product was zero initially. As the reactants were decreasing, they were converting into what? Into products. So initially, a lot of product was being formed, right? A lot of product was being formed, and then it started to form less product per unit time as more reactants converted. And then the product's concentration also became what? Constant, right?
Yep.
What does a flat line over here mean? That the
That it became
concentration of
constant.
the product is not changing, right?
Yep.
The product, after a certain time, it wasn't changing on the y-axis. The reactant decreased a lot initially because a lot of product was being formed. But after a certain time, its line also became flat. That means it wasn't changing on the y-axis, right? So the point or the time where both these lines had become flat, after that time, what is happening to the concentration of reactants and products? Are they changing after this time? Yep.
The
Are the
same.
changing, are the concentration of reactants or products changing after this time t over
No,
here?
they remain the
It's not
same.
changing. Now they are constant with respect to time,
Yep.
right? The reactant and the product, this is the product line, sorry. The product remains constant. The reactant's concentration remains constant, but has the reaction stopped? Has the reaction
No, it's
stopped?
still going on.
The reaction hasn't stopped. The equilibrium has been established. The products and the reactants concentration have become what? They have become constant. Their rates are same, right? The forward and backward reaction, their rates have become constant. Equilibrium has been established, but now the amount of product and amount of reactants, they're not changing anymore because they're now at equilibrium, and equilibrium needs to maintain these levels. So what is the time where dynamic equilibrium was achieved over here? The time or the line where both these graphs, the reactant graph and the product graph, have become flat. This is the time where dynamic equilibrium was achieved. All right.
Yep.
What is this point over here? This point of intersection.
Where they have the same
Yeah, they
concentration.
have the same concentration, not constant, because even after this point, they both were changing, right? They both were changing still after this point. The reactants were decreasing, the
Yep.
products were increasing, right? So this is the point where reaction concentration is equal to products concentration, but they're not at equilibrium right now, right? Where is the point where they're both at equilibrium? When they're not changing anymore. And what was the time where they stopped changing? This was the time. This is the time where dynamic equilibrium was achieved. Are we clear?
Yep.
Okay. So a fun fact about the dynamic equilibrium graph, or a very easy identification for the dynamic equilibrium graph, would be that this graph is always symmetric. You'll find a symmetric graph. That means you can fold the graph onto itself from the middle and it will be identical from both sides. Or if you cut it from the middle, you'll find two identical sides. So can we look at that over here? Do we see that over here?
Yep.
So this dynamic equilibrium graph should be identical. Why? Because when we divide this graph, this side should be 50% and the other side should be 50%. Just like we said in the reaction rates, the forward and backward rates would be same. It's just an identification for dynamic equilibrium. You can also make a graph for other equilibriums, but let's write some points over here. Whenever you're trying to identify the graphs, you need to know that reactant concentration, square brackets mean concentration, okay? Reactant concentration is maximum at time zero. Product concentration is minimum or zero at time zero, right? Now, as reaction proceeds, what should happen to the concentration of the reactants? Yep,
Decreases.
it decreases. And what should happen to the concentration of the products? Starts
It
increasing.
increases.
Yep. At equilibrium, what should happen to the reactants concentration and products concentration?
Remain constant.
It becomes constant, does not change. Does not change anymore. And what about the products concentration? Constant,
Also
does
constant.
not change anymore. That's when you know that equilibrium has been established. All right? Are we clear?
Yep.
So for a dynamic equilibrium graph, let's write a note. The graph of dynamic equilibrium is symmetrical. All right?
Yep.
But we can also make graphs for other equilibriums of just equilibrium. Let's just write equilibrium. So their graphs would look like this. For example, if more products are formed and less reactants are formed per unit time in the forward and backward reaction, the reactant line again is maximum at initially, product initially is minimum, right? Let me zoom in. Now, what happens is reactants convert more into products, but the products are more and the reactants consume are less. So this graph would not be symmetric. Let's say 70% forward and backward direction is 30%. You will not see a symmetric graph in other cases of equilibrium. All right? Or
Yep.
you could see a graph like this, where less product is being formed, but more reactants are being consumed. It could be like this. It's again not symmetric. Only the graph of dynamic equilibrium, let's say this was 40% and this was 60%. All right. So for any other equilibrium, the graph would not be symmetric. But for dynamic equilibrium, you'll see a very symmetric graph like this. And you should be able to identify the time at which dynamic equilibrium was established. That is when both lines have become completely flat, or both the reactants line and product line, which are representing the concentrations, become what? Constant. They not change anymore. That's the point where dynamic equilibrium was established. Clear?
Yep.
So this was the graph for dynamic equilibrium. Now let's write some important points or a summary for today. Let me make a box first. Let's make a box. These are important points that I want you to remember. Important points. So the first point would be that in order for equilibrium to establish or for a reaction to be reversible, what's the first condition? Yes, for a reaction to be reversible so that it can proceed in the forward and backward direction, what's the first condition? What should the
The
system be?
concentration should be constant.
That's when equilibrium is established. What's the first
The
condition?
rate should be constant.
Nope. The first condition is that the system should be
Oh, closed. Yeah.
closed system. Yes, exactly. So the system, let's say equilibrium can only be established in a reversible reaction if the system is a closed system. This is the first point. In a closed system, a reaction can be reversible, and in a closed system, equilibrium can then establish. All right. And what was a closed system? Nothing can be added. Nothing can be added or removed. Nothing can be added or removed from the system apart from energy. All right.
Yep.
Another important point was that at equilibrium, the quantities of everything, the quantities, let's say concentration, and I'm referring to concentration over here, okay? Or amount or mass is quantities of reactants and products. At equilibrium, they should be what? Yep,
Constant.
yep, they are constant. So at equilibrium, there are quantities of reactants and products in the reaction mixture remain what? They remain constant. But does that mean if they're not changing, does that mean for a reversible reaction or at equilibrium, does that mean that the reaction has stopped?
No, it doesn't. It still
No,
continues.
exactly. constant, although the reaction is still continuing. It is still continuing in the forward and backward direction. In the forward and backward directions. The reaction continues, it hasn't stopped. But the amounts or quantities of the reactants and products, now they will not change when you've reached equilibrium. They will be maintained at that level. Are we clear?
Yep.
Okay. Now the third part or the third point will be linking the next topic to our equilibrium that we've studied up till now. And that is, if you disturb this equilibrium, if we disturb this equilibrium by changing any condition, by changing any conditions, what should happen? What do you think should happen if we disturb this equilibrium? Any conditions such as temperature, pressure, or concentration all affect equilibrium. And the other point should be, if equilibrium is disturbed, if equilibrium is disturbed by any condition changes, it will always try to re-establish itself. All right.
Yep.
If we disturb this equilibrium by changing any conditions, what would happen? First, we need to know
It gets
that conditions
disturbed.
such as temperature, pressure, or concentration all
Yep.
affect equilibrium, because any equilibrium establishes at a certain temperature and pressure, and then it decides a certain concentration of reactants and products to exist at that equilibrium.
Yep.
Once you've disturbed any one of these things, the equilibrium is now removed. The equilibrium is no longer equilibrium because the conditions have been disturbed. An alert has been, it is now alert, and now what does it want to do? It wants to re-establish equilibrium. How does it do that? That's Le Chatelier's principle. That's our next topic. All right.